Okay, this is tutorial 4 of the point set topology course. Um, this is like tutorial 4. So this is 20th August. So in this tutorial, we will basically discuss half of the time. We will discuss the assignment 3 problem, and next half of the time, mostly we will discuss the week 4th content. I mean, basically 4th week's contents and the problem related to those. So first assignment 3 we will discuss. So assignment 3 first question is which of the following intervals of R intervals of R is or are closed, and what are the in standard topology of R? Standard topology of R. And options are like A is closed 0 1 to 1 open, B 0 1 closed at 1, C 0 to infinity, and D none of this. Okay, so here what is that? First recall the definition of a closed set. Recall. Let X tau X be a topological space. A is a subset of X. Then A is called, or A is said to be closed if X minus A is open in X tau X. That means X minus A is an element of tau X. This is the thing. Okay. Now let's first take A, option A, check option A, this one. So whether this is closed or not, how can I check if the complementary is open? Now R minus 0 to 1, this is equals to minus infinity to 0, union 1 to infinity, closed 1 to infinity. Then we can see, we know that at open sets in R are basically open intervals and their union. Here particularly minus infinity to 0 is an open interval, but 1 to infinity is not an open interval. Okay, this is not an open interval. Also, you can look at in different way. Let's take 1 belongs to minus infinity to 0, union close 1 interval to 1. Then for any epsilon greater than 0, we can easily see that 1 minus epsilon 1 plus epsilon, this particular portion does not contain in this main set, that union of 1 to infinity. But if this is open set, then we should able to find an epsilon greater than 0 such that 1 minus epsilon 1 plus epsilon should be a subset of this set, but that is not happening. Why this is not happening? For example, take epsilon is equals to half. Okay, then 1 minus epsilon by 2, which is equals to 1 minus 1 by 4, which is equals to 3 by 4. Then 3 by 4, this does not belongs to minus infinity to 0, union closed interval 1 to infinity. That means, for example, we can take this one, but for any epsilon we can take, but I will always find an element such that this element is not here. So that means minus infinity to 0 union 1 to infinity is not an open set. Okay, so 0 1 is not closed. The whatever I have done for the point 1, we can do the same thing here. So let's take r minus 0 1, which is equals to minus infinity to 0 union 1 to infinity. Whatever thing we have done here for 1, for example, we can do for 0 point. Similarly, we can say that. Similarly, we can say that minus infinity to 0 close union 1 to infinity is not open. That means 0 to 1 is not closed. That means this is not closed, this is not closed. Now similarly we can say that 0 to infinity is not closed, because as r minus this 0 to infinity, this is equals to minus infinity to 0, this is not closed, sorry, this is not open, not open. Okay, so this is also not closed. That means this is the only option. It is the only option which is correct. That means none of this. That means none of the options, basically first three options, is not closed. Okay, I hope it is clear there. Just a minute. Okay, yeah, it is okay. Now, now if I take now questions two. What questions is there? Which of the following subsets of R square is closed in standard topology? Okay, standard topology of R square basically. What are the options? Option A, H is equals to all points AB belongs to R square such that B is greater than or equals to 0. Option B is H plus, which is equals to all point AB belongs to R square such that B is strictly greater than 0. Option C is the circle which is equals to all those AB belongs to R square such that A square plus B square is equals to 1, and D is S1 union H plus. Note that we already proved that this set is closed. Okay, we already proved that this set is closed, proved in previous class, proved in previous class. How it is proved basically? How it is proved? Just define f from r square to r by f of a comma b, which is equals to a square plus b square minus 1. This is being polynomial in a comma b, f is continuous. Okay, now f is continuous, then inverse image of every open set is open, then pre-image of every open set is open, and pre-image of every closed set is closed, and pre-image of every closed set is closed. Now we know that this set is closed. Okay, I can take this 0. 0 is closed in R. Then f inverse of this particular set this one, which is equals to basically all those a b such that a square plus b square 0 minus 1 is equals to 0. That means this is equals to 1 is closed. Okay, now so that means this is closed, this is closed. But what about these two set that I will do is simultaneously. Let's define f from r square to r by f of ab is equals to b. This is projection. Okay, clearly this is projection. Now we already seen that projections projection is continuous, then f is continuous, right? Now f is continuous and this particular set, my this set 0 to infinity is closed in R and 0 to infinity is open in R. Now f being continuous, f inverse of this closed interval, this is equals to all those a comma b belongs to R square such that f of ab which belongs to closed interval 0 infinity is closed, because this set is closed. So that means this is equals to all those AB belongs to R square such that B is greater than is equals to 0 is closed. Now similarly, if you look at the pre-image of the inverse pre-image of 0 comma 0 to 0 to infinity, that is equals to all those AB belongs to R square such that f of AB which is belongs to 0 to infinity. That means this is open and not closed. Why this is, that is I am writing, which is equals to all those AB belongs to R square such that B is positive. B is positive. Okay. So this is also you can see in different way, and this is not closed. Why this is not closed? You can take some, you can just shortly I will try to, this is from graph. If you write this is x-axis, this is y-axis, and if you write this is the portion, this is the portion with this particular line, this is for, this is the h basically, right? Now if I take only the above portion without the axis x-axis, then this is h plus. Now if you take circle, the circle we already proved that this is closed. Now if I take circle, what is circle basically? That is, okay, this is the circle. Now circle, this is h, sorry, this is S, this is S1, this is also closed. But what S1 union of H plus, that means this circle with this red region, but this is not closed. Why this is not closed? If I take any point on the x-axis, then there I will get a sequence coming from the set above or red region, and which converges to this point. But if a set will be closed, if it is a set will be closed if and only every limit point should be there, at least, sorry, a set will be closed if and only a closer to a, that means if xn converges to x, then x should be there, a set is closed. Okay, if it is closed, now, okay, I will not write. Basically basic point is that we can take a point here which is not in S1 union H plus, and that point is not in S1 union H1, but we can get a sequence from the S1 union H which converges to that point. But if S1 union H is closed, so that point should be in S1 union H, but that is not. So that means S1 union H is also not closed. So S1 union H plus is not closed. Okay, I hope it is clear why S1 plus H is not closed. Now the third question. Third question says that Okay. Third question says that which of the following which of the following subset or subsets of MNR is or are closed in standard topology. Option A, all orthogonal matrices which is equals to all A belongs to MNR such that A transpose A is equals to identity. Second, all SLNR that is equals to all those A belongs to MNR such that determinant of A is equals to 1. This is already we have checked once this is closed. Still I will discuss today that GLNR such that all those A belongs to MNR such that determinant of A is not equals to 0, and D option GLNR plus which is equals to all those A belongs to MNR such that determinant of A greater than 0. Okay, still this is already we have proved. Still I will discuss today. What is the main idea is that already we discussed B is closed. Similarly we can show that C is also closed. How it is basically defined? If you look at that, let f is a function from Mn R to real number R with standard topology on both sides. How it is defined? F of A is equals to determinant of A. This is being polynomial. F is continuous, right? F is continuous. Now, as F is continuous, pre-image of closed set is closed, right? So let's take pre-image of closed set is closed. Let's take 1. Okay, yeah, 1. This is closed set in R. Now F inverse of this 1, what is this? This is equals to all those A belongs to MNR such that determinant of A is equals to 1. Okay, now this is closed, so this is then closed set. Similarly, so this is closed set. What we got? Sorry, C. Similarly, we can show that. Similarly, we can show that C, comma D are open. How we can show that? Now, F inverse of this particular 0 set, since 0 set is closed, that is equals to all A belongs to MNR such that determinant of A is equals to 0. This is closed as 0 is closed, but if you look at all A belongs to MNR, this is equals to determinant of A not is equals to 0. This set is basically nothing but MNR minus F inverse of this 0 set. But this is closed set, F inverse of 0 set. This is closed set, so complementary will be open set. This is open set. So this is particularly open set. Similarly, if you look at this particular thing, that f inverse of 0 to f inverse of 0 to infinity, this is open. So this will be open. This is equals to all a belongs to MNR. All a belongs to MNR such that determinant of a belongs to 0 to infinity. This is open because f is continuous, and 0 comma 0 to infinity, this is open. This is equals to all a belongs to MNR such that determinant of a is positive. This is open, right? Now the last option, option D. What option D says is that GLN plus R. Okay, so no, sorry, option D is correct. So that means this is open also. That now the first option, that orthogonal matrix. So for option A, what will define? That will define F from MNR to MNR. F of A is equals to A transpose A. Then we have seen that F is continuous and the singleton set ID is closed in MNR, because this is singleton set and MNR has standard topology, that is topology of R to the power n square. So that will be closed set. Then F inverse of this particular ID, which is equals to all those A belongs to MNR such that A transpose A is equals to ID, this is closed. So this is also closed. So these two are closed, these two are open, these two are not closed. Now come to the point of question 6. Okay, let A and B be subsets of a topological space X and Y. Here X and Y are two different topological space and A and B are two subsets. Choose the correct options. Option or options? What are the options? Let A cross A closure cross B closure is equals to A cross B closure. B option is A closure cross B closure is subset of A cross B closure, and C is A closure cross B closure is superset of A cross B closure, and D is none of this. So here if we try to look at this as A B union, that means basically what I want to make, that A closure union of B closure and relation with A union B closure, then these two are equal or not, that we don't know. Sorry, these two are equal or not, that we have already discussed, but this way will not work here. Okay, this type of pattern will not work here. So we have to think a little differently. Okay, now here what is the thing is that if we can prove the first one, then automatically B and C will be correct. Okay, so and also you can see that proving B and C is equals to proving the A, that is same thing. Okay, so if I can prove A, so that will be, that means basically if I can prove B and C, then that will give A is true, B is true, C is true, and D is, then automatically it will be false. Okay, now how we will prove this actually? How will prove this? Proof will be say like this way, like for example the sketch will be something like for any xy belongs to capital X cross Y with product topology. If xy belongs to A cross B closure, then for every open set, and we know that in product topology open sets are like U cross V is also a one type of open set. Let U be an open set, let X belongs to A closure B. Now what I want to prove that let X belongs to A cross B. So what I want to prove that that X belongs to A closure. I want to prove that X belongs to A closure, Y belongs to B closure. That means you have to prove that for every open set U of X containing X and V of capital Y containing Y, U makes non-empty intersection with A, V makes non-empty intersection with A. And okay, now let's U cross V is an open set in X cross Y product topology. Now, as this is open set, so U and also let XY belongs to this. Okay, so basically this will be like this way. Let U belongs to tau X, V belongs to tau Y, such that X belongs to U, Y belongs to V. Now U cross V is open in X cross Y, and XY belongs to U cross V. That means U cross V makes non-empty intersection with A cross B. That means there exists A comma B, which is belongs to U cross V intersection A cross B. That means there exists A belongs to U cross A and B belongs to V cross B. That means U intersection. Sorry, that means there is U intersection A and V intersection B. That means U intersection A is non-empty and V intersection B is non-empty. That means X belongs to A closure and Y belongs to B closure. In this way, you can say, okay, there is a problem, I think. So just give me 1 minute. Yeah, sure. Thank you. For a subset A, for a subset A of X, closure of A, X belongs to, for a subset A of X, an element X belongs to capital X is called, is said to be, is said to be in X A closure. That means X is sitting inside A. If for any open set U U of A, U in open set U containing X meets A or makes non-empty intersection with A, makes non-empty intersection with A. That means for any open set U coming from topology of the set X, such that X belongs to U, then this U should makes non-empty intersection with the set A. Then we can say that X is belongs to A closure. This is the definition. Now we will prove this one by definition. Okay. Now let's take X is belongs to A closure cross B closure. Okay. Sorry, there are 2 points, not single points. X comma Y. That means X is sitting inside A closure and Y is sitting inside B closure. Y sitting inside B closure. Then for any open set U belongs to tau of the topology, subspace topology. Here topology of the A is subspace topology, and no A or B subsets of a topological space X and Y. Okay, so basically, so no, sorry, so this is coming from X. Sorry, this is not A subspace topology. This is U is coming from tau X and V is sitting inside. That means they are open in X and Y respectively. That is what I mean. Such that for any open set U and V, X belongs to U, Y belongs to V, then such that then U intersection A makes non-empty intersection and V intersection B makes non-empty intersection. I think this is clear. If this is clear, there exists an point A belongs to U intersection A and B belongs to V intersection V. There exists A and B belongs to V intersection B. That means A comma B that is sitting inside U cross B and A comma B also sitting inside A cross B. Now, what I want to show, what I have taken house dot property. No house dot property. Here we are not going to any house dot property. First of all, what I want to make sure that maybe what your confusion here, A is subset of X and B is subset of Y. These two space itself are different. Okay, X and Y as a topological space they are different. We can take X to be real number. We can take Y to be some abstract space, right? That is not related to even real number. Okay, so and in house dog there is something like two different open set, something like taking 2 point. We want to make something two open set which contains each of them and they are disjoint. There is disjoint is one important factor. Here is, I mean, don't be confused with house dog. If it is not clear, even you can ask. But the here, what is that? A is a subset of X, B is subset of Y. We know that X cross Y has a subspace topology, right? Now A cross B is a subset of X cross Y. Now, as a subset, A cross B have as a subset of X cross Y, A cross B have closure. So that closure, how that closure is related to A closure and B closure? That is the question. Okay, I hope question is clear. So now what I am doing from definition, take any point X, Y coming from A closure cross B closure. That means X coming from A closure and Y is coming from B closure. Okay. So now if X is coming from A closure by the above definition, there exists for every open set U of tau X such that X belongs to U intersection A is non-empty, and similarly for every open set V belongs to tau Y such that Y belongs to V intersection B is non-empty. Right. That means this set being non-empty, U intersection A, there exists an A belongs to U intersection A, and there exists an B belongs to V intersection B. I don't know why my screen is changed. Just 1 minute. Yeah. Yeah. So A is coming from here and B is coming from here. So AB is coming from U cross B and BB is coming AB is coming from A cross B as well. So now A and B is actually sitting inside U cross B intersection A cross B. Okay. Now we want to show that AB is sitting inside A cross B closure. Okay, how we will show this? Now, for any, no, not X, this X cross Y, X comma Y, X comma Y is sitting inside of that. Now, for any open set, let's take UVW. For any open set W of X cross Y with product topology, such that X and Y is sitting inside W, there exists a basic open set, there exists and a basic open set U cross V. Okay, such that U is coming from tau X and V is coming from tau Y, such that X comma Y will sitting inside X comma Y belongs to this U cross V and this U cross V will sit inside W. Then as U intersection U cross V intersection A cross B is non-empty, as A comma B is sitting inside U cross V intersection A cross B. So that means this A comma B is sitting inside W intersection A cross B. That means W intersection A cross B is non-empty. Then for any open set W of x cross y containing small x comma y makes non-empty intersection with A cross B. So that means this x comma y is actually sitting inside closure of this A cross B. That means what we got, that if x belongs to A cross and y belongs to B closure, that means if this one, then x comma y is sitting inside A cross B closure. That means A closure cross B closure, subset of A B closure. First of all, up to this point, is there any doubt? Please tell me. Because if that is clear, then other part will also be clear as it is. Is there any doubt?
No doubt, sir. Clear.
Clear, na? That how I am just constructing an open set. This basic thing, you just recall from this basic thing, that for any open set W of the product topology x cross y, there should exist a basic open set such that this Wx should contain from W. But basic open set of the product topology, if you recall that U cross V, U is coming from tau x and V is coming from tau y, and that will form the basis. So if that is forming basis for any open set W, there should exist, and U basis open set U cross V, this one will hold. I think this is the something I am recalling. What the basic main property I am recalling, that for an topology Ax comma tau x, suppose this is a standard usual topological space, and B of tau x is the basis. Then for every open set U of Ax, for every open set U subset of X, there should exist a basic open set Wx, and X belongs to U. There should exist a basic open set Wx such that X should be in W and Wx should contain in U. This is the thing. But for product topology x cross y, this basis is nothing but the product of this type of. U is coming from tau of x and V is coming from tau y. This is the basis for the product topological space. If this is basis and W is an open set containing x comma y, so there should exist a basis open set, and that basis open set is something like U cross V. And for any U and V, such that U is coming from tau x and V is coming from tau y, and X is sitting inside U and Y sitting inside V, I can get this type of thing, that there should exist an AB which is sitting inside U cross V intersection A cross V. So this is the main idea. Okay. Now conversely, now I will prove the converse part. What converse part says is that, so now what we have proved, just A closure cross B closure, subset of A cross B closure. But then now I want to prove the converse part, A B closure, subset of A closure into B closure. Similarly, I will show this way how that so what it says, that which option is correct. What it says, that you have 6 sorry, says that A closure subset of B closure. This means B is correct. If I can prove C is correct, then A automatically will hold. Now let X comma Y is belongs to X comma Y is an element from the product topological space X comma Y, such that this XY actually closure of AB. Okay, then I want to prove that X is in closure of A and Y is in closure of B. That is what I want to prove. Now as XY is sitting inside A cross B closure, then for every open set W of the cross product topology, okay, such that X comma Y is sitting inside W, then this W intersection A cross B should be non-empty. That means there should exist A comma B, that A comma B may be XY, that A comma B can be XY, that doesn't matter. Okay, but but we can say non-empty means there should exist some point. That point need not be always x comma y, but that point can be x comma y. How I am saying this point? That suppose I am taking 0 comma 1 interval, then 0 is not in the 0 comma 1 interval, open interval, right? But there, for every interval, sorry, every open neighborhood of 0 makes non-empty intersection with 0 comma 1. So that point, so that means that every open set U which makes non-empty intersection, every open set U of 0 which makes non-empty intersection with 0 comma 1. So this is non-empty, so that point is not 0. So but that can be 0, but that point is not 0. But here it is not 0, that's what I mean. Okay, now A comma B is sitting inside W intersection A cross B. That means A comma B is sitting inside W and A comma B is sitting inside A cross B, right? Oh, sorry. I am going to wrong direction. I think this way I will not be able to prove. Okay, I have to take some specific. No, sorry. This way I will not be able to prove. Okay, I have to take specific. Let U be an open set such that X belongs to U and V belongs to V be an open set in Y such that Y belongs to V. Then this U cross V is an open set in the product topology, open set in the X cross Y with product topology, and X comma Y belongs to this U cross V. Okay, I hope this is clear. This X comma Y belongs to U cross V. Okay, now what I want to show here is that as U cross V, yeah,
Sir, X belongs to U as well as V, na?
no. X belongs to U, Y belongs to V. Okay, my
Okay,
writing
sir.
is
X belongs
confusing.
to U and Y belongs to V.
Huh. This is all. I just, for example, I want to what I want to prove. Okay, let me clear what I want to prove. Xy belongs to A closure B closure. I want to prove X belongs to A closure, Y belongs to B closure. That is what. Then X comma Y will be A closure cross B closure. Right? That.
Okay, sir. Okay, got it.
Don't be confused with union or intersection with this cross. Cross means that's ordering, nothing special. Union is some different thing. Okay, so what I want to say, then let U be an open set from coming from X and V be an open set coming from Y such that X belongs to U and Y belongs to V. I want to prove that this U and V makes non-empty intersection with A and B respectively. Then we can say that X is in A closure, Y is in B closure. Right? That is what I will prove. Okay, but as XY belongs to U cross V and U cross V is an open set in the product topology, as open set in product topology, U cross V makes non-empty intersection with A cross B, that is non-empty. That means there should exist a point A comma B which is belongs to U cross V intersection A cross B, right? Okay, this is not bar. Okay, here this intersection A cross B. That means A is belongs to U intersection A, B is belongs to V intersection B. Okay, this is ordering. A comma B is sitting inside U comma B, means A is in U, B is in V. Again A comma B sitting inside A cross B, that means A is in capital A, B is in small capital B. So that means U intersection A is non-empty and V intersection B, that is non-empty. But what we have started, that for any two open set such that, okay, just let me write it clearly. For any two open set U coming from tau of X, V coming from tau of Y such that X is belongs to U and Y is belongs to V, we have proved this. That means X is in the A closure, Y is in B closure. That means X comma Y is sitting inside A closure to B closure. That proves that A cross B is subset of A closure, B closure. That implies option D, C is correct. C is correct, and that implies A is correct. Is it clear?
Clear,
Is
sir.
it
Got
clear?
it.
Okay. Now next, what is the next question? I think 10, right?
Yes, sir. 10. Number 10.
Okay. What number 10 question says? Okay, this is very interesting problem. Okay, let X be a matrix space with matrix D. Let X comma D be a matrix space, and that matrix will give a topology. That matrix will generate a topology. That topology, we are talking about that topology specifically. Okay. Now, for any non-empty set A of X, define the distance map. Define the distance from X to A as follows: d of Ax is equals to infimum of A belongs to A, d of x A. Question is, consider the topology on X induced by the matrix. Consider the topology on X induced by the matrix. Okay. Consider topology on X induced by the matrix D and standard topology on R. Standard topology on R, right? Then the map. Question is, then the map BA from X to R. First of all, A always continuous, always continuous. B is continuous if and only, sorry, only if, not if and only if S has discrete topology. C is continuous if X has trivial topology, and D none of this. None of this. So if we can prove the first one, that always continuous, then there is nothing with, because nothing is special condition. If X has trivial topology, X has trivial topology. Okay. So if I can prove that first condition, then I think other is no need, right? Because here it is saying that this only thing does not affect. I think there is also problem. I think only if, yeah, right. That should be written. That is what I am missing. Only if. So if I can prove that this function is always continuous, whatever topology we may have, then these two we don't need to check differently, because these two are not correct then. This means that when this means these two condition is saying that when X has discrete topology, only then if this function is continuous, but that is also not correct. And when it has trivial topology, only then function is continuous, that is also not correct. This function is always continuous, whatever topology the Tx may be have. Okay. And that is coming from discrete topology. So that is coming from the topology generated by the metric D. Okay, so we will prove the F is, we will prove that for any metric, D, DAX is continuous. That is what I will prove, right? That is what I will prove. So now what I need to say that here is a metric on the left hand side and right hand side real number. Okay. So function is here dx. Just let me write again dx. What dx? That is infimum of what is a coming from a and subset of d of a x. This is the function. Okay. Now what I want to prove is that for every epsilon greater than 0, if a function f from x to r is there, okay, if a function, let f is a function from x, just recall, I'm just, this is I'll write in recall center, recall, if f is a function from x to r, be a function, then f is said to be continuous at x belongs to capital X if inverse image of every open set is open. That is the thing. If pre-image of every open set is open under F, that means for any epsilon greater than 0, F inverse of this B epsilon of f of x is open. Am I writing correctly? F is a map from Acto, and this inverse image of every open set is, just let me 1 second please. Correct. Okay, so this is basically not this pre-image of every open set is correct. So basically, what is open set here means that I'm coming for any epsilon greater than 0, f inverse of of uh, f inverse of this is an interval. That what interval that is f of x minus epsilon comma f of x plus epsilon. This is the basic open set in real number, right? These are the basic open set in real number. This should be is open. That means when a set will be open in a topological space where topology is generated by the metric. Now this is sitting inside X, right? And X has a topology which is generated by the metric D. So now what I want to say that, so this is open, that means this particular set will be open, and that is containing fx. Okay, this particular set contains x. So now x belongs to f inverse and f of x minus epsilon comma f of x plus epsilon. This is the thing. And f inverse of f of x minus epsilon comma f of x plus epsilon will be open. That is open if there exists an b delta x. B delta x means the neighborhood of delta radius centered at x, that is sitting inside f inverse of f of x. Okay, this is the thing. So that means what I need to prove, that means for any z belongs to this b delta of x, f of z should be sitting inside f of x minus epsilon to f of x plus epsilon, right? That means what I need to prove, that f of z minus f of x is less than epsilon. Is that clear up to this point? I have not even started the problem. I have just make sure that what we need to prove, this particular thing. What do we have to prove, that function f is a function, then I have to prove that f is continuous. That means f inverse of every open set is open. I am trying to prove that f is continuous at x. So that means f inverse of the open set. What is the open set here? F inverse of open set containing the point fx. Okay, what is the containing the point of fx here? Basically, fx minus epsilon comma fx plus epsilon. This is the point containing fx. So inverse image of that set is basically this one particular this set. Now, if this is the inverse image, this is the inverse image, I have to prove this is open. To prove this is open, what I have to prove? That there exists a delta such that this b delta x containing here, and for any that is containing here, so that means for any z belongs to this, fz should sitting inside here. So fz should sitting inside here if and only mod of fz minus fx less than epsilon. That means we have to prove that for every epsilon greater than 0, that means we have to prove that for every epsilon greater than 0, there exists a delta greater than 0 such that when z is coming from this b delta of x, this b delta of x, I just make sure what b delta of x. Already I have taken x, y, z, so I will take some different indexes. B from coming from x such that d of b and x is less than delta. This is the thing. This is the b delta x such that for when z belongs to s, this dA of z minus dF of x mod should be less than epsilon. That is what I need to prove, right? So now that is what I need to prove. Now for any up to this point, is it clear? Then I will just do some easy calculation. Is it clear up to this point? You can even collect with the real analysis. This is just a function.
Yes, sir. Clear.
Okay. If it is connected to real analysis, this is very easy. I am just coming to back to the real analysis type of things. Okay. For any now, okay, for any z belongs to this b delta x, what I want to prove that this dz of a, and for any a coming from capital A, we can write this one is a dz of x dz of x plus d of x. Z is coming from there. Z is okay. Z is right. I'm writing correctly. This one. Okay. Now, so this is less than equals to. This is not equal. This is less than equals to. By triangle inequality of metric B. Every metric must satisfy the triangle inequality. So this is the triangle inequality, and this is true for every A belongs to A. That means infimum of A belongs to capital A such that d of ZA is less than is equals to dzx plus infimum of A coming from capital A, d of xa, right? That means this will be d of dA of z. This will be like dA of z, which is less than is equals to dzx and plus dA of x, right? That means dA of z minus dA of x. This is less than is equals to dzx, but z is coming from the b delta x. Okay, as z is coming from b delta x, so this distance must be less than this distance must be less than, where is the this distance must be less than delta. Okay, now as z is in the b delta of x, that is equals to all those b belongs to the set x such that distance from b to x is less than delta, then x is also sitting inside the b delta of z, which is equals to all those b belongs to x such that d of bz is less than delta. That is very much clear. I think that is not a big deal. So now we will do the same thing for x belongs to this. Now d of now for any a belongs to capital A, dxa, which is less than is equals to dxz plus dz comma a. Now again taking infimum of all a belongs to capital A, d of xa less than is equals to d of xz plus infimum of all a belongs to capital A, d of za. This is possible because this dz metric is always positive, non-negative, not positive, non-negative. Okay, that's why this less than equals to and infimum all those things is possible. D of a x, which is less than is equals to d of xz plus dA of z. That means this dA of x minus dA of z, which is less than is equals to dxz, which is less than is equals to, this is less than delta, because x is coming from the b delta z, and b delta z means all those elements such that d of b comma z is less than, that means in particular d of xz is less than delta. This should satisfy. So that means if you look at this particular thing and this particular thing, what we got basically that mod of dax minus mod of daz, which is less than is equals to d of xz, d of xz. Now for any epsilon greater than 0, take delta is equals to that epsilon. I have to choose the delta, na? But I am choosing delta as the epsilon. Then when x, when z is coming, when z is coming from the b delta of x, then the mod of dA of x minus dA of z is less than is equals to d of xz, which is less than delta, which is equals to epsilon. So that means dA dot function, this function is continuous at z, sorry, at x, because that is what the definition says that. Is it clear? If there is any doubt, any line, any doubt, just say it. I will try to explain again.
No, sir, it's clear, but it is taking a lot of time to digest.
Okay, is it clear now? Just thing is that I just want to make sure that consider f is same as d of ax. What I want to prove is that I want to prove that continuous at x. First, whatever I have written, if you are not able to understand here, so at least try to read after this class once, and if there is any doubt, write me. I will try to explain again. Okay, now problem is that what my point is that what I just basically what I want to prove is that suppose f is the function here, f is the function here, f is same as d of a. D, don't confuse with this particular a particularly. Okay, dA. Now, now what is that I want to prove that f is continuous at x. Then what I have to prove that for every epsilon greater than 0, there should exist an delta greater than 0, such that whenever z is coming from b delta of this particular x, mod of f of x minus f of z should be less than epsilon. This is what I want to prove, right? This is what I want to prove. Now for every epsilon greater than 0, I have to find the delta greater than 0, but I am choosing delta as actually the epsilon and taking b delta x means b epsilon x. This is the same epsilon, and then I am just proving these two particular inequalities, these two particular, this one and these two particular inequalities, which gives that mod of f of x minus f of z is less than epsilon. I hope if it is, I hope this is the sketch. If still there is any problem, you can write me or you can ask here. I will again discuss. Okay, and on the basis of this problem, there is the next problem is on the basis of this actually. I hope next exercise that is of that is assignment 3, that is I think um, 11. 11 is on the basis of this particular problem. This is 10. 11 is on the basis, and answer of 11 will be C closed if and only for an x belongs to capital X, dcx equals to 0. Okay, except 15, is there any other problem I can discuss? Any other for any other person even? I'm going to 15, but because I think 11 is also important. I don't know if you are correct, then this is very standard problem, 11. Okay, if there is no any other specific, I'll go to at least 15, and again if there is any time and if there any okay, then we can think whether 11 will do or go to the go to the weak force content. Okay, so let's go to 15. I don't know 15. I will try. Okay, yes.
Sir, can I tell you how I thought about 11? Question 11.
11 is there.
Sir, actually, my thought process was like this. It says C is closed if and only if DC of x equals to 0 implies x belongs to C. So if a subspace has to be closed, it
Hmm.
means that every
Distance.
intersection,
Okay.
every limit point has to be in set itself.
Right.
So,
That will be give one
so
side.
yeah, so this will give me one side. And on another side, if we see DC x equals to 0,
Hmm.
that
And X is
means
closed.
the,
Sorry, C is closed.
yeah, that
This
will give me C is
then you
closed.
have no, you have to first one that what you are saying is that C is closed if and only for an x belongs to dcx equals to 0 implies x belongs to C. First take C
Yes,
is
sir.
closed and dcx equals to 0. Then you have to show that x is belongs to C. That
C.
means if you can okay just 15 I am just writing shortly. First of all the set x belongs to capital X such that dcx is equals to 0. This is same with C closure. Okay, you have to show this one. Okay, now if x C is closed, now if C is closed and x belongs to capital X such that dcx is equals to 0, that means you can show that x belongs to C closure because that is the thing. But C is closed, that means C closure is C. That means x is belongs to C. That is one side, right?
Yes, sir,
Sorry,
one side.
yeah, this is if I'm not making any mistake. This side is C closure and take C is closed and x is belongs to dcx equals to 0 and okay dcx equals to 0 implies that x belongs to C closure. That means x is in C. That is one side. I think that is what you were saying. I think no, you were saying reverse direction. Now conversely, you are saying that if x is coming from the x and dcx is equals to 0 implies x is belongs to C. Okay, then I can show that actually x is not in C. X is belongs to C closure. Okay. Sorry. I think I am making confused. Okay, let's clear me. Okay, what Vivek you were saying first? Please tell me. I just have to listen and then I will try to.
Give me a second, sir. I'm going to the question. Sir, the second part means if x belongs to C and distance of x from the set C equals to 0 implies x belongs to C. So, what I thought was if x belongs to C and distance of x from C itself is 0. So, if suppose I take y as a limit point,
Okay,
so every
right.
neighborhood of y will intersect C itself
Right.
apart from x.
Yeah.
So the distance as we move to y, the distance will be zero. The sequence will converge to zero eventually. So distance of y from C will converge to zero.
Right. So y will be in closure of. Right. Y will be in
Yes,
closure.
y will belong to C eventually.
Yeah, but y is in also C, so that will be closure actually. Yeah. Right.
Yeah, yes, sir. Yeah.
Okay. Let me just will write it shortly. If I'm not making any mistake, just 1 minute. Question 11. What first is that now C is closed. Let C is closed. Okay. Now there is one specific things. What is that things? This dcx is equals to 0. This dcx, this means what is infimum of all. What is the definition here? All a belongs to C. I'm taking the same symbol d of ax, right? This is the thing. That means there exists a sequence for any infimum or supremum. There exists a sequence an and coming from C such that this d of Can C is closed and dcx equals to 0. Suppose C is closed, I am proving the C is closed and then proving that if dcx equals to 0, then x is actually in C. That is what my target. Right now target is that if x is closed and dcx equals to 0, then I will prove that x is actually in C. That is what I will prove. Or enough to show that x is in C closure, because C is closed, right? What I want to prove that, to prove that x is belongs to C, that means enough to prove that x is belongs to C closure, because C is closed, that means these two are same. I think this is what I want to prove. Now if this is equals to 0, then there exists a sequence A and C such that DC of AN is equals to, yeah, there exists a sequence AN coming from coming from C, such that D of this AN comma X is equals to 0. This is definition of infimum or supremum, whatever. If the forget about looking at these things, this is 0 means there exists a sequence coming from AN coming from C such that D of AN X equals going to be 0. That means AN is going to be going to the point X in X with the topology coming from the metric D, because that is the definition of a sequence, whether it will go converge to or not, right? That means this X is inside the C closure. What is C closure? C closure is actually limit of all those points. If you remember that X belongs to C closure if and only, okay, just I'll write here also. Uh, recall Recall, X belongs to C closure if and only if there exists a sequence Xn coming from C such that Xn converges to X. This is the thing. So we got a sequence An which converges to X, and An is sequence from C. That means this X is basically in C closure, right? So first part is, and that is actually C. So that means X is basically C. So when C is closed, and then in that situation if dcx is 0, then we will get that x belongs to C. So one side is clear. I hope this is not a problem. Now for the other part, conversely, if x dcx is equals to 0 implies x belongs to C, we want to show x belongs to we want to show C closure is equals to C. That is what C is closed. That is what I want to prove, right? That means C is closed. Proving this one is enough to show C closure is subset of C, because C is always sitting inside the C closure, right? C is always sitting inside C closure. So enough to prove that C closure is subset of C. That is enough. Now we will prove a claim, basically claim. What the claim is, I am making that all those x belongs to S for which dc of x is equals to 0, this is same with the C closure. But what assumption is assumption says that what assumption is writing in quoted line, that x belongs to capital X and dc of x is equals to 0 implies x belongs to C. That means the shade x belongs to capital S such that dcx is equals to 0, those shade is always sitting inside C, because that is what the assumption. If you just write there is if and only if term, and left hand side is says that C is closed, and right hand side is says that x belongs to capital X, dcx is equals to 0 implies x belongs to C. This is the thing, na? This is the thing, x belongs to C. So one side is clear, C is closed, this will imply this particular thing. Now I want to prove that this particular thing will imply this particular thing. Now how will prove that? This particular set, all those x for which dcx is equals to 0, this set is sitting inside C, that is giving, because if x satisfies this particular condition, then x is sitting inside C, that is giving. That means this set is subset of C. So now if I can prove that this set is nothing but C closure, that means C closure is subset of C. Is it clear? So enough to proving the claim. So that is what my point is that. So enough to proving the claim, the above claim, this one. Is it clear? I mean, I'll prove this one, but is it clear that why enough to proving the claim? Because what it says that this is the assumption that if x belongs to dx such that dcx equals to 0, then x must be in C. This is the assumption. X should be in C. Now, this particular condition is nothing. This particular condition is nothing but this particular set. That means this particular set is subset of C. But if I can prove that this particular set is nothing but C closure, that means C closure is subset of C. And this is the same thing. So now I will prove that C closure is subset of this claim is proving this claim is that x belongs to capital X such that DC x is equals to 0 implies C closure. That is what I have to prove. Okay. So let x belongs to capital X. Okay, and DCAX means is equals to infimum of all A belongs to capital A, C, K belongs to capital C, D of AX. That is some same logic. That is equals to 0. That means there exists a sequence AN belongs to C such that D of AN comma X is equals to 0. That means AN converges to X. That means X is inside C closure. That means this particular set X belongs to capital X such that DCX is equals to 0. This is subset of C closure, which already we proved in previous, but still okay. Now let other part is very easy, just little bit of thinking or nothing special. Let Y belongs to C closure. Need to prove D of CY is equals to 0. This is enough to proving this one. But as Y belongs to C closure, there exists a sequence. This is if and only that there exists a sequence AN coming from the set C such that AN converges to Y. That means D of this A1 converges to Y in XD. This convergence is not in real number. This is in matrix space. That means D of AN comma Y that converges to 0. Same thing. AN converges to Y in matrix space means D of ANY converges to 0. This is in real number. If you note that metric is positive real number, so this is in real number. Okay, yn converges to Y is equals to 0. Now let's assume now just let's say me what will be this infimum of then not now then infimum of D A Y, this particular A coming from A, what will be this infimum? This infimum can't be any other thing except 0 because this is positive. These all are positive. Suppose this is a particular collection of sets and that is positive, and there is a sequence which is converging to 0, then what will be the infimum of that set? That set will be 0. This is 0 because this is 0 as because why this is because if you take this particular real number collection A comma Y such that A is coming from A, this is set of non-negative real numbers because metric is non-negative real number always non-negative real numbers, and there exists a sequence D of AN comma Y belongs to this particular set such that D of AN comma Y is going to be 0. Okay, sequence D of N comma Y such that D of N comma Y is going to be 0. That means infimum of that set is can't be 0 bigger than 0. Is it clear? I am just saying that if you take a non-negative real number set, okay, non-negative, 0 can be even a member, and take infimum, and if there exists a sequence which converges to 0, that means infimum can't be except 0. Infimum has to be 0. Is that
Yes,
is
sir.
that fact clear? Okay. So now as
Got it.
this yeah So as this is 0, so that means d of a y, sorry, d of a y is equals to 0. That means y is basically on that particular set, that x belongs to capital X, such that d of ax is equals to 0. That means C closure is subset of this particular set. I think now it is wholly proved. I'm just, these things are not that much big. I'm just proving very explicitly to writing everything, every single point. You can skip many things to prove, because I'm just writing many things many clearly. I just main point is to write everything clearly. Okay, now come to the last question. At least I don't know I will get time, but let's do as fast as possible. 15. A map and your connectedness. At least I will discuss your connectedness of matrix in okay, connectedness, that path connected and connectedness, that I will at least discuss. Okay, let a map f from x to y between topological space is called open map. Okay, function is a map is called open map if it maps called open map if it maps if it maps open set to open set to open set, right? Now let T is a map from R to the power m to R to the power n be a linear transformation, be a linear transformation, m n positive integer, then T is surjective if and only T is open. So question is that T is surjective if and only T is open. So question is that whether this statement is correct or true or false. Answer is true. So I am not writing true or false. I am just proving this one. That is what I mean. Okay. This question is very interesting. Why this question is interesting? This question is something very much directed to the open mapping theorem. When you will read function analysis in master's course, so you will read open mapping theorem, and this is very much is a simpler version of open mapping theorem, you can say. Sorry. Simpler version of open mapping theorem. Okay, let's read the open mapping theorem. Yeah. Okay, what it says that first is that T is surjective if and only if T is open. Okay, let's just 1 minute. I just let me think a little bit. I don't think T is surjective if and only if T is open. First of all, if T is not surjective, then image of T is okay. Image of T is vector space. That is the property of linear transformation. If T is linear transformation, then image of T is a vector space. Okay, that is not, there should not be any doubt that is from vector space thing. Now if T is if it is vector subspace which is not open. So question is, if T is open, that means T maps open set to open set. T is open, then T is surjective. That first I need to prove. Why? This is one thing. I think that is not T is surjective. Okay, this is not proved hopefully. Okay, let T is open, then T is surjective. I have to prove. If T is not surjective, that means there exists a point. Just let me think a little bit. If T is not surjective, there should exist a point which was left by R to the power n. Just a minute, 1 minute. T is open, then T is surjective. This is very easy thing. I don't know why this is not clicking to me right now. When T is surjective. If T is not surjective, if T is not surjective, M may be less than N. Well, no. This is not help. There nothing is mentioned. Idea is that if T is not surjective, then T of the R to the power M, I think, yeah, R to the power M is not equals to R to the power N. Okay, but R to the power N is open. So that means T of R to the power M will be open set. But open set in R to the power N is, okay, please give me 1 minute. 1 minute. 1 minute will be enough. Just 1 minute. Got it. Okay. Basically, thing is that here I think one thing is uh, not 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 considered that much. Okay, let me just write. Okay. The idea is main problem is that, okay, just let me. If T is open, then T is surjective. If T is not surjective, if T is not surjective, then, okay, T is not surjective, then T of R to the power n. This is proper subspace of R to the power n, but and T being open map, and R to the power n is open, then T of R to the power n is open, right? This one is open set. Now the fact is that if you want, then I will prove this fact. I just that that fact is that interior of a proper subspace of a nonlinear space is empty. So this is the thing, that interior of a proper subspace, I mean, basically thing is that any proper subspace can't be, and T of R to the power m is a subspace. This is a vector space. Okay, now this subspace is not topological space sense. Okay, this subspace is not in topological space sense. This is R to the power n and R to the power m. These two are vector space, right? Vector space means vector space with addition and scalar multiplication. In that sense, it is vector space. Now, as this is vector subspace, so better to write it is vector subspace. This T R to the power m is a vector subspace. Vector subspace of R to the power n, right? So T R to the power n is open, and T r to the power n is vector subspace. So my claim is that, or fact is that, this is very standard fact. Fact is that there is no proper empty set in a proper non-empty rectangle. Basically, fact is that there is no proper in non-empty, proper non-empty open set in R to the power n. That is what I mean. Okay. So what I want to say, that T is open, then T is surjective. Why I want to T is not surjective, then T of R to the power n is a proper subspace of R to the power n. But T open map and R to the power n is open set. That means T of R to the power n is open. Also, T being a linear map, T being a linear transformation, T of R to the power m is a vector subspace. So fact is that there is no proper and non-empty open set in R to the power n. Should I prove this fact, or I will just leave it?
So we
Then
can leave it for now.
I think that will be better, because I just want to go little over. Okay. So now, then, that means that either T should be zero map or T should be full map. I mean, range of T should be full space. So that means T of R to the power m is equals to R to the power m. That means T is surjective. Basic fact is that I mean, this is the fact that if I take, there is no proper invariance open subspace, not subset. This is the fact. Open subspace, open vector subspace of R to the power n. I mean, if it is open and non-empty, it can't be subspace. Proper non-empty, it can't be subspace, because this is subspace. Then, I mean, idea is that suppose this is a this is I'll just write the shortly what the idea. Non-empty open vector space. Suppose this is open, there is no non-empty open and vector subspace. These are two facts, and non-empty and proper. So now, if it is open, then any point A belongs to the suppose this is the set A which is open and vector space, and A is a point. Then for every epsilon greater than 0, the set, if I take norm of A minus X is less than epsilon, all those X belongs to the set X or A, such that this one less than, this is an open set sitting inside A. But any point which is even not in A, any point which is not in even A, that point can be written. I mean, we can scale it as small, such that that point is again inside the B. I mean, what will be that scaling? That scaling will be like scaling. I just write now B by. Okay, let me just scaling. I'll just write the scaling only. Yeah, scaling is that for any B, we can take a new vector B is equal to like A plus some R less than 1 by 2 of norm of B. Norm of B means here metric. Norm of B means root under of summation of Bi square, mod Bi square. This is the norm. Norm in R to the power n. And that is the metric. That is the standard metric uh, in R to the power n. Okay, this one. Now this vector will satisfy this particular condition. Okay, this vector will satisfy this particular condition, and this I can take R is as epsilon by, this is epsilon. This vector will satisfy this particular condition. You can show this vector will satisfy particular condition, and then U will be inside A, but U is a vector space. So if U is a vector space, U and A is an U is a vector space, not U. This is A is a vector space, and A belongs to capital A. So that means U minus A belongs to A. That means epsilon by 2 norm B into B. This is B. B is in A. That means B is in A, because scalar multiplication again is in subspace, and A is in subspace. That means any point outside any point that we have started that B is not in A, right? B is not in A, but that point is end up with an B is in actually in A, because the subspace property. That subspace property is something very not direct to, I mean, not allowed to give that a proper non-empty subspace. Okay. So this is rough. I will just circle it. I will not write anything. This is rough. I'll not even erase this one. So this is all. And one side. This is one side. So now for other side, what other side says that, okay, on the other side, that if T is open, then T is surjective, right? I think this side proof is there. Should I prove that? Other side proof that T is open, then T is sorry, other side
No,
proof
sir.
means, yeah, if T is surjective, then T is open. That is what I mean to prove. I think that is in written in solutions space, right? So I think I will just
Yes, it.
leave right now because there is 20 minutes left. I will try to discuss problem from there. Okay. If it is not clear, I will write me. Just read once. If it's not clear, write me. I'll try to discuss next class or in personally. Okay. Okay.
Okay, sir.
Now, okay, I'll try to. Okay, your question I will discuss. Don't worry that much time I have taken. Now from the week four content. Week four content. Okay. Week four contents, from week four's content, what the basic definition is that as said, I'll just take two definitions: connectedness and path connectedness. Connectedness. Let X, that definition I'll just recall. Let X tau be a topological space, then X is called connected. X is called connected if there exists a non-empty proper open set A, or equivalently non-empty and proper, very two important fact, or equivalently there exist A and B, two non-empty, proper is no needed because one is non-empty, other will automatically non-empty disjoint open set. Disjoint means A intersection B is empty. Open set such that A union B is equals to X. These two are same. You can easily look at how I am saying. Okay, let me just, what it says is that, first part says is that X tau be a topological space, then X is called connected if there exists non-empty proper open set A, open set A in X tau, or equivalently there exist two non-empty open set and disjoint, which are disjoint such that A union B is equals to X. First part, okay, you can say if the second part is happening, that at that if second statements holds, then we can take the A is non-empty and B being non-empty, A is proper. A is proper. Okay. So that means the first part is, so first statement, and if first statement holds that if there exists a non-empty open set A, non-empty and proper, that means X mod B, X mod A is again non-empty and proper, is non-empty and proper. Okay. And why it is open? Because its complement, okay, maybe, okay, if I'm not making any mistake. Sorry. Right. This is both open and closed, not open set, open and closed. That's in open and closed A. So now A is proper and A is open. So X minus A is open again. That means this is A, this is B, non-empty, and proper. Now A being open, A intersection X minus A is non-empty and A comma X minus A are open. Both of them are open. So first condition and two condition are second are same. Now path connected. What path connected says that X tau be a topological space, topological space. 2 point X and Y belongs to capital X is called X tau is called topological space X tau is called path connected if for any 2 point x comma y coming from capital X, there exists a continuous function if from 0 1, I think that is in general denoted by gamma 0 1 to capital X such that gamma of 0 is equals to x, gamma of 1 is equals to y. So basically what it is says that X tau will be a topological space, then X tau is called path connected if for any 2 points X and Y there exists a continuous function gamma from 0 1 to X such that gamma 0 is equals to X and gamma 1 is equals to Y. This is basically means that there exists a connected path from X to Y. Continuous path. Basically, there is a continuous connected path from X to Y. Now, first fact, if a topological space, if a and all this definition will hold for subspace also with subspace topology, subset with subspace topology. Now, if a topological space is path connected, then it is connected. If a topological space is path connected, then it is connected. Then it is connected. I think I will not prove this one. If there is any doubt, obviously I will prove connected. But the converse need not be true. Look into the example. I think lecture example. Which lecture it is? Lecture number. I just need to. I just want to mention the lecture number. I think lecture 19. Is it lecture 19? No. It is lecture 18. No. It is lecture 17. No. Lecture 20. It is lecture 20. Look into the example of lecture 20. Okay. Up to this point, this fact, is there any doubt that definition of connectedness and these two factors same and path connectedness, and if a topological space is path connected, then it is connected, but the converse need not be true. Okay. This is in general. Okay.
No doubt, sir.
Okay, no doubt. Now I will just rapidly look at into the lecture 16. Is there any zenith? Your question will come, don't worry. I mean, basically, why I just did not take that much time here, because uh, here not much exercise this time is given in. Okay, so one more fact I want to. Any interval, interval means real. Interval is connected. R to R is connected. Next fact is that if x tau x, y tau y is connected, then x cross y with product topology is connected. Connected. Then R to the power n is connected. That is what I want to make you. Okay. If x and y topological space, x cross y with product topology is connected. That is very interesting proof you can look at. Topological space, then x is connected if and only if x are homeomorphic. This another fact. Homeomorphic if x and y are homeomorphic. Homeomorphic means, again, there exists a bijective continuous such that inverse is also continuous. Okay, homeomorphic, then x is connected if and only if y is connected. And the circle is also connected. Fact. Sn means all those x1, x2, means this is pair basically. x1, x2, xn coming from real numbers such that summation of xi square is equals to 1 is connected with subspace topology. Connected with subspace topology. I think lecture 7, no, lecture 8. Lecture 8. It has only one connected. Okay, connected components are closed and bounded. Sorry, not connected components are not connected. Equivalent classes of the connectedness. Equivalence classes of connectedness relation are connected and closed. Closed and connected, but for path connectedness, it is connected but need not be closed. It is path connected but need not be closed. And one of the important fact is that x and y are connected and x intersection y is non-empty, then x union y is also connected. Here x and y are subspace. Okay. Okay. Now your question is that GLNR, SLNR, right? Those things. Let's come with those points. Okay. Now one more fact that I have not used. F is a map from x to y, be a continuous function. X and y are two topological space. F is a continuous function. Okay. If x is connected, then f image, then f of x with subspace topology, subspace topology is not connected. Sorry, is connected. Is connected. But what your point you asked, that is not correct. At least you can see from here that if y is connected and f is continuous, that does not imply that x will be connected. Right? That example, I think, if you look at this one, 2, 2, 3, this is not connected. But define a function from here to real number, just constant function 5. This is constant function, and this set 5 with the subspace topology, this is singleton set that is connected, and inverse image of 5 is the full set which is not connected. Okay, so if f is continuous and y is connected, then f x need not be connected. Okay, now using this particular thing, what we will show here is that, now consider to show that GLNR is not connected. I have not written even plus GLNR only. How? This let f is a map from GLNR to real number. How this is defining? Okay, I think there is one more important property, one more fact is that if f is surjective, then y is connected. Okay, just let me write that one also. Let fact f from x to y is continuous and surjective, continuous and surjective, then y is also connected. Okay, now let f is a map from GLNR to real number, f of a is equals to determinant of a, right? Then you can see that image of f is equals to basically all real number minus 0, because GLNR is all those sets where, note that GLNR is all those elements a coming from MNR such that determinant of a is non-zero, right? So but if GLNR is connected, then what I will okay, basically what I will to prove that this is not connected. Okay, that I will to prove that. Now 0 to infinity and minus infinity to 0 are two open set in R with standard topology. Now f inverse of R minus 0, this is same with GLNR, right? Because this is the image actually. R minus 0 is the image, and that is same with f of 0 comma infinity union of f inverse of minus infinity comma 0, right? Now f being open map, f being continuous, f f inverse of 0 comma infinity and f inverse of minus infinity comma 0 are open in GLNR, and also f inverse of 0 comma infinity and f inverse of minus infinity comma 0, these are non-empty. Obviously non-empty. There we can find a matrix whose determinant is positive and whose determinant is negative. We can find, right? We can find just a matrix whose determinant is positive, determinant is negative. That is always can be found. Okay, for any n, I think. So that means this set f inverse of minus infinity to 0 and f inverse of 0 to infinity, they are not a non-empty, because this set is all those elements where the determinant is positive, and this set is all those elements where determinant is negative. Those are non-empty and open set. Okay, non-empty open set, and Also disjoint. Also they are disjoint. Intersection f inverse of minus infinity to 0 is empty. That means GLNR is disconnected. I hope it is clear, right? Is there any doubt proving that GLNR is disconnected? Next is that,
No, sir.
okay, thanks. Next is that ON is equals to all those matrices which are orthogonal such that A transpose A is equals to identity, right? Here is also, we know for an orthogonal matrix A, determinant of, or real orthogonal obviously, for any real orthogonal matrix, determinant of A is equals to +1 or -1. Similarly, define f from ON to R by f of A is equals to determinant of A. Then f inverse of only singleton set 1 is equals to all those element A belongs to ON such that determinant of A is equals to 1, and f inverse of -1 all those element A belongs to ON such that determinant of A is equals to -1. Then we can see that these are non-empty, these are open as f is continuous, and -1, 1, these set are open in standard topology of open. That I'll just write. Now -1, 1 are open in the standard topology, in the standard topology of the set -1, 1. Note that this -1, 1 as a subset of real number, the subspace topology of real number, which is standard topology, that is, for that topology, this singleton set are open. But when I will consider real number with the full space topology, with usual standard topology, then those single point elements are not open set. Okay, so that means these are all open set. So inverse image of that means f inverse of we will just 1 minute. And these two, f inverse of -1 and f inverse of 1 are open and disjoint, and their union is basically full is equals to ON. So ON is disconnected. Yes, Vivek, yes, you can say.
Sir, can you please repeat how -1 and open? Sorry, -1 and 1 are open in standard topology now.
-1, 1, these are as a singleton set, they are not open in. Okay, sorry. There, what my point is that now take A is a real number, take R is a real number, right? Take R is real number. Now this
Yes, sir.
-1 and this singleton set what are closed. Singleton sets are closed in standard topology because except this one point -infinity to 1 and 1 to infinity, we can write union of these two set, complement of 1. Complement of 1 can be written union of these two sets, and these are open set, right? So that's why
Yes, sir.
that's
That
why
is what I
that's why
was
one is
thinking.
closed. Yeah, that's why one is closed. Singleton sets are closed, but they are not open in standard topology. Okay, but standard topology of R. But when I will consider -1, 1 as a subset, this is the set A, and I want to consider standard topology of A. And what is the standard topology of A? A is a subset of R. Then standard topology of A is equals to A intersection of open sets U coming from the standard topology of R. So means what is that? That if U contains 1, then that will make intersection with A will make 1. If it contains -1 only, then that will give -1. If it contains 1 -1, that will give A. If does not contains 1 or -1, that will give empty set. So these are only possible open sets in standard topology of -1, 1. Is it clear, or should I repeat one? Because there is very
No,
interesting and
sir.
important thing. Okay, so why
No,
in
sir.
standard
Got it now.
topology of why in standard topology of -1, 1 singleton sets are closed, but sorry, singleton sets are open, but they are not open in the standard topology of R. Similar reason that integers are open, set of integers, singleton sets are open in the set of integers with standard topology. So that's why 1, -1, they are open set in the topology of -1, 1. In topology of the space -1, 1 with standard topology. Okay. So basically, these topology are same with the topology of real number, but as set are different, so they are different. Okay. Is this clear? I think, okay, just 1 minute. I will look at is there anything I need to define or discuss. Otherwise, I will. I think this weekend not much exercise is there in notes, class notes. So that's why I have taken little less time in this particular portion. Okay, I think there is not that much. Okay, is there any specific doubt? Okay, if there is no any specific doubt, I will then stop. Okay, subject. Okay, English. So if there is no any specific doubt, so I am just closing. I'll stop here. Okay.
Thank you, sir. Thanks a lot.
Okay.
I got the
Thank you.
connectedness now.
Okay, if Vivek, if there is any more problem of connectedness, because connectedness is very important topic, and I today I think I have not prepared too much to which I have not. I should have prepared some questions from connectedness separately, but that I have not prepared. So whatever questions lecture notes that I have tried to solve. Okay, I will try to discuss as much questions in the next tutorial of connectedness and top connectedness. Okay, thank you. I'll stop here.
Thank you, sir. Good night.
Yeah, good night.